There is something out there. Not a metaphor, not a fear. A real, physical object. Massive, cold, and ancient. Moving silently through the outermost darkness of our solar system. We have never seen it directly. We have never photographed it. No telescope has captured its light. And yet, the evidence for its existence grows stronger with every passing year, pulled from the behavior of distant worlds that seem to know something we don't. Something is out there, bending the architecture of the solar system's edge in ways that defy coincidence. And if it's real, if Planet 9 truly exists, then everything we thought we knew about how this solar system was built will need to be rewritten from scratch. This is not science fiction. This is planetary science at its most thrilling and most humbling frontier. This is the story of a ghost world. A planet so far away that it completes one orbit around the Sun every 10,000 to 20,000 years. A planet so cold that its surface temperature hovers barely above absolute zero. A planet so massive it may hold the gravitational fate of our entire outer solar system in its invisible grip. And the wild part? We found the first whisper of its existence not by looking outward, but by noticing something strange about the way a handful of tiny, frozen worlds were moving. Let's go back to 2014. The Outer Solar System Origin Survey had been cataloging small icy objects, the remnants of the early solar system, orbiting in the region beyond Neptune, in the vast, frigid expanse known as the Kuiper Belt. Astronomer Scott Shepard and his colleague Chadwick Trujillo were reviewing data from the Subaru telescope in Hawaii when they spotted something deeply peculiar. They had found a small object called 2012 VP113, a world about 450 kilometers in diameter, nothing exceptional in size, but its orbit was unusual in a way that stopped them cold. The orbit of 2012 VP113 had an argument of perihelion, a technical way of saying the angle at which it makes its closest approach to the Sun, of around 340 degrees. That number alone would have been unremarkable. But when they compared it to a handful of other extreme trans-Neptunian objects orbiting far beyond Neptune in elongated, tilted paths that took them to extraordinary distances from the Sun, they found that all of them seemed to cluster together in orbital space. Their perihelia, their closest approach points, were all bunched up. They were all pointing in roughly the same direction. In a randomly distributed solar system, this should not happen. Given the gravitational influences at play, Neptune's pull, the galactic tide, the slow drift of solar perturbations over billions of years, these distant objects should have their orbital angles spread randomly around the Sun, scattered in all directions like seeds thrown to the wind. The probability of finding 6 of them clustered together by pure chance was calculated at roughly 0.007%. That is not a rounding error. That is not noise. That is a signal. Shepard and Trujillo published their findings and cautiously proposed that some unknown object, perhaps a distant planet, might be gravitationally shepherding these small worlds into their suspicious alignment. It was a careful suggestion, buried in technical language, but it set off a chain reaction in the planetary science community that has not stopped since. 1 year later, in January 2016, Caltech astronomers Konstantin Batygin and Mike Brown dropped what can only be described as a scientific bombshell. They had taken the clustering hypothesis seriously, run detailed computer simulations, and concluded that the orbital alignment of these extreme Kuiper Belt objects was not just unusual, it was nearly impossible to explain without invoking a previously unknown planet. A large, distant, and real planet. They called it Planet 9. Their models suggested it would be roughly 10 times the mass of Earth, somewhere between the size of Earth and Neptune in physical dimensions, orbiting in a highly elongated ellipse that takes it anywhere from 200 to 1,200 astronomical units from the Sun. For reference, 1 astronomical unit is the distance between the Earth and the Sun, roughly 93 million miles. Neptune, the outermost recognized planet, orbits at about 30 astronomical units. Planet 9, at its closest approach, would be nearly 7 times farther away than Neptune. At its farthest, it would be retreating to distances so remote that the Sun, the burning star that defines our solar system, would appear as nothing more than a bright point of light in the sky, indistinguishable at a glance from just another star. Think about that. A planet in our own solar system so far away that the Sun looks like a star. A world that has been silently completing its glacial orbit for billions of years without any human civilization ever knowing it was there. Even the ancients who mapped the night sky with extraordinary precision, The Babylonians, the Mayans, the ancient Greeks who cataloged thousands of stars had no way of knowing about it. It is simply too faint, too far, too dark to see with the naked eye or even with most modern telescopes. We know it is likely they're not because we have seen it, but because of the shape of the gravitational shadow it casts on everything around it. The gravitational mechanics at work here are, frankly, beautiful in their complexity. Planet 9, if it exists, orbits in an ellipse tilted at roughly 15 to 25 degrees relative to the plane of the rest of the solar system. Its elongated path carries it in an orbit roughly anti-aligned with the clustered Kuiper belt objects, meaning that while those small worlds have their perihelion points clustered in one direction, Planet 9's own perihelion points in the roughly opposite direction. This is exactly what you would expect from a massive body gravitationally hurting smaller objects over long timescales. Planet 9's gravity would have spent billions of years nudging those small worlds into resonant orbital configurations, locking them in a kind of cosmic choreography where they are protected from gravitational destabilization precisely because of where they orbit relative to the giant planet. It is the same physics that governs the relationship between Neptune and Pluto. Pluto's orbit is resonant with Neptune's. For every 2 orbits Neptune makes, Pluto makes 1.5. And this resonance means Neptune's gravity never directly kicks Pluto out of the solar system. The relationship is stabilizing, rhythmic, mathematically elegant. Planet 9 and its retinue of distant small worlds would operate on the same principle, just at timescales and distances so enormous that human comprehension strains to hold them. But the evidence doesn't stop with the clustering of extreme Kuiper belt objects. There is a second, deeply strange phenomenon that Planet 9 could explain, and it concerns the very tilt of the solar system itself. The 8 recognized planets all orbit the Sun in roughly the same flat plane, the plane of the ecliptic, which formed from the original protoplanetary disk of gas and dust that surrounded the young Sun about 4.6 billion years ago. But here is something that has quietly puzzled astronomers for decades. The planet's orbital plane is actually tilted by about 6 degrees relative to the Sun's own equatorial plane. In other words, the Sun is slightly off-kilter from the rest of its own solar system. The Sun spins on an axis that is tilted about 6 degrees away from being perpendicular to the plane in which its planets orbit. This is strange. Everything should have formed from the same rotating disk of material, and that disk should have been aligned with the Sun's equatorial bulge. So why the 6-degree discrepancy? Theorists have struggled with this for decades. And then Badigian and Brown ran the numbers for Planet 9. If a planet of the right mass exists in the right highly inclined, highly elongated orbit they proposed, its long-term gravitational influence on the rest of the solar system would naturally produce exactly this 6-degree tilt over billions of years. Not approximately, not in the right ballpark, exactly 6 degrees. At this point, a scientist is justified in sitting back and feeling a slight chill run down the spine. When a single undetected object can simultaneously explain the orbital clustering of distant small bodies and the mysterious 6-degree tilt of the entire solar system, you are no longer looking at coincidence. You are looking at convergent evidence from completely independent lines of inquiry, both pointing at the same conclusion. That is how science works at its most powerful. That is the feeling of closing in on something true. And there is more. Because Planet 9, in Badigian and Brown's models, also explains the existence of a peculiar population of objects in the Kuiper belt that orbit in the exact opposite direction from everything else, what are called retrograde orbiting objects. In a normally arranged solar system, small bodies should orbit in the same direction as the planets, carried along by the same angular momentum of the original protoplanetary disk. But a handful of objects with extreme orbits have been found circling the Sun backward. Planet 9's gravitational influence, acting over billions of years, would produce exactly this retrograde population, tossing some Kuiper belt objects into high inclination, reversed orbits through a mechanism called secular resonance. Once again, the simulations match what we observe. By the time Badigian and Brown finished cataloging what Planet 9 would explain, the list had become almost uncomfortably long. The orbital clustering, the 6-degree solar tilt, the retrograde population, and the existence of a class of objects called detached Kuiper belt objects whose perihelia are so far from the Sun that Neptune's gravity could not have put them there, but Planet 9's gravity could have. It is the kind of explanatory power that, in the history of science, has almost always preceded a major discovery. You have to understand how rare this is. In the history of planetary science, predicted planets have been found only twice before based on gravitational anomalies. The first time was in 1846, when astronomers predicted the existence of Neptune based on anomalies in Uranus's orbit, and then found it within 1 degree of the predicted location within days of beginning the search. The second time was when Percival Lowell predicted the existence of Planet X in the early 20th century based on supposed anomalies in Neptune's orbit, but that prediction turned out to be flawed. The anomalies were measurement errors, and the eventual discovery of Pluto was, in retrospect, a lucky coincidence of direction rather than a genuine gravitational prediction. Planet 9 represents a third attempt, and unlike Lowell's Planet X, it is backed by far more rigorous statistical analysis and independent lines of evidence. This also raises a deeply philosophical point about how science builds knowledge. We are entertaining the existence of a world larger than Earth, lurking in our own solar system, based purely on mathematics, statistics, and the subtle misbehavior of distant frozen objects. We have not touched it. We have not photographed it. We have not even bounced a radar signal off it. And yet the confidence of the prediction has steadily grown, not because of wishful thinking, but because each new piece of data from the outer solar system seems to fall in line with what you would expect if Planet 9 were real. Science is, at its core, the process of letting the universe speak and then listening carefully enough to hear what it is saying. Right now, the universe seems to be whispering the name of a world we have never seen. Now, who is actually leading this search, and what does it actually look like to hunt for a planet this remote? Mike Brown is perhaps the most fascinating figure in this story, and not only because of Planet 9. He is also the man who killed Pluto, or more accurately, who inadvertently triggered the process by which Pluto was reclassified as a dwarf planet. In 2005, Brown and his colleagues discovered Eris, a distant object in the outer solar system that turned out to be nearly as large as Pluto. The discovery forced the astronomical community to confront an uncomfortable question. If Pluto is a planet, then why not Eris? And if Eris, then why not the dozens of similar-sized objects we keep finding out there? The International Astronomical Union convened a vote in 2006 and decided that both Pluto and Eris would be classified as dwarf planets. Brown famously embraced his role in Pluto's reclassification with good humor, even writing a book titled How I Killed Pluto and Why It Had It Coming. And now he is the man who may be responsible for discovering that our solar system has a real 9th planet after all, lurking in the darkness at incomprehensible distance. There is a certain poetic justice in that. Brown and his collaborator Konstantin Batygin, a theorist who brings a deep command of orbital mechanics to the partnership, have been coordinating a systematic search using the Subaru telescope on Mauna Kea in Hawaii, one of the most powerful ground-based instruments in the world. The challenge they face is enormous. Planet 9, depending on where it currently is in its highly elongated orbit, could be anywhere from 200 to 1,200 astronomical units away. At those distances, even a world the size of Earth would appear fantastically faint in a telescope image. The reflected sunlight reaching it would be so attenuated by distance that it would return from its surface as the faintest possible glimmer. You are not looking for a bright dot in the sky. You are looking for a pixel, maybe less than a pixel, that moves very slightly from one observation night to the next. This is needle in a haystack searching at its most extreme. The sky is enormous. The object is faint. Its motion from night to night is almost imperceptible. And the Milky Way's dense band of background stars makes searching certain regions of the sky particularly difficult because there are simply too many other points of light contaminating the images. It is painstaking, expensive, and deeply uncertain work. And yet Brown and Batygin keep looking, because the statistical weight of the evidence tells them that patience will eventually be rewarded. Other teams have joined the hunt as well. The Dark Energy Survey, an enormous sky survey originally designed to study the large-scale structure of the universe, has turned part of its attention toward the outer solar system and has been collecting data on distant trans-Neptunian objects. The Outer Solar System Origin Survey in Canada has contributed dozens of new Kuiper Belt objects to the database. The Panoramic Survey Telescope and Rapid Response System, known as PanSTARRS, has been scanning large areas of sky and has turned up new candidates. Every new extreme trans-Neptunian object discovered is another data point, another vote either for or against the existence of Planet 9, depending on where it is and how it is orbiting. And here is where the story becomes genuinely complicated, because the evidence is not entirely unambiguous. Some astronomers have looked at the same orbital data and concluded that the clustering effect may be at least partly, or even entirely, explained by observational bias. The argument goes like this: we do not survey the entire sky uniformly. We tend to look in certain directions at certain times, using telescopes located in the northern or southern hemisphere that have limited sky coverage. If the objects we have found are found preferentially because of where our telescopes are pointing, then their clustering in orbital space might be an artifact of how we looked, not a signature of something pulling on them gravitationally. This is a serious and legitimate scientific concern, and it should not be waved away. The history of astronomy is full of phantom signals that turned out to be selection effects, quirks of how observations were made rather than real properties of the universe. Brown and Badigian have acknowledged this possibility and have worked to account for observational bias in their analyses. Their conclusion is that even after correcting for known biases, a statistically significant clustering signal remains. But other researchers, most notably a team that published detailed analyses of the Dark Energy Survey's uniform sky coverage, found that when they looked at a region of sky they had surveyed systematically, the clustering effect diminished. Their conclusion was that observational bias might explain a larger portion of the signal than Brown and Badigian believe. This is science working exactly as it should. Competing teams, different data sets, rigorous arguments, no consensus yet. The truth is, the question of whether Planet 9 exists has not been definitively settled, and anyone who tells you otherwise in either direction is overstating the certainty of the current evidence. What is settled is that the outer solar system shows unusual patterns that demand explanation. Whether that explanation is a giant planet, a primordial black hole, some unusual distribution of smaller objects, or observational bias that has not been fully characterized, that remains genuinely open. And that openness, that live, unsettled quality of the question, is exactly what makes it one of the most exciting frontiers in planetary science today. Let us pause on that primordial black hole idea for a moment, because it is not a fringe theory. It was proposed in a serious academic paper published in 2019 by Jakob Schultz of Durham University and James Onwin of the University of Illinois, and it deserves more than a passing mention. Their argument is elegant and unsettling in equal measure. They noted that if a small primordial black hole, formed in the very early universe, long before any stars or planets existed, had been captured into orbit around the Sun, it would exert exactly the same gravitational influence on the outer solar system as a planet of similar mass. It would create the same orbital clustering. It would explain the same anomalies. And it would be extraordinarily difficult to detect, precisely because black holes, unlike planets, do not reflect light. You cannot see them by reflected sunlight. How would you even begin to search for a primordial black hole in the outer solar system? The answer involves looking for the faint glow of what is called Hawking radiation, the theoretical quantum mechanical emission of energy that all black holes produce as they slowly evaporate, combined with the occasional flash of light that occurs when the black hole's intense gravity causes distant background light to briefly brighten through a process called gravitational microlensing. The Vera Rubin Observatory, set to begin its full legacy survey of space and time operations in the coming years, may be capable of detecting these microlensing events if the primordial black hole hypothesis is correct. As of now, neither the planet hypothesis nor the black hole hypothesis has been ruled out by observation. We are in the peculiar position of not knowing whether the anomalous object at the edge of our solar system, if it exists at all, is a planet or a black hole. The universe is not obligated to be simple, but let us return to Planet 9 as the planet, because even the question of how it got there is deeply fascinating and surprisingly contentious. The solar system's architecture today is the result of billions of years of gravitational chaos, migration, and rearrangement. The four giant planets, Jupiter, Saturn, Uranus, and Neptune, did not form where they orbit today. The NICE model and its successors, frameworks developed over the past 2 decades to explain the dynamical history of the outer solar system, proposed that the giant planets underwent dramatic orbital migrations during the early history of the solar system. Jupiter moved inward. Saturn, Uranus, and Neptune moved outward. During this migration, the outer solar system was violently rearranged. Small bodies were scattered. Orbital resonances were crossed. The late heavy bombardment, a period of intense asteroid and comet impacts on the inner solar system recorded in the ancient craters of the Moon, may have been triggered by this migration event. Where does Planet 9 fit into this picture? There are several competing scenarios. In one, Planet 9 formed in the inner solar system, in the region where the gas giants formed, and was gravitationally scattered outward by interactions with Jupiter or Saturn during the period of planetary migration. This is actually not as unlikely as it sounds. Computer simulations of early solar system dynamics suggest that this kind of scattering event was common. The young solar system likely formed multiple large planetary embryos, and gravitational interactions between them would have ejected many of them entirely from the solar system. Most of the ejected worlds would have left the solar system entirely, becoming rogue planets drifting forever in interstellar space. But a small fraction, perhaps a few percent, would have been scattered into highly elliptical orbits that kept them loosely bound to the Sun at enormous distances. Planet 9, in this scenario, is a survivor of the solar system's violent early history, a world that escaped ejection by the narrowest of margins and has been silently orbiting in the deep freeze ever since. In another scenario, Planet 9 formed in the outer solar system, in a region where the protoplanetary disk was cold enough for ices to condense and planetary embryos to grow. Models of planet formation in the outer disk suggest that this is possible but difficult. The material is too sparse and the timescales for accretion are very long at extreme distances. Planet 9 might have formed relatively quickly during a period when the Sun was still part of its birth cluster. A dense grouping of young stars whose collective gravity might have helped shape the outer solar system in ways that no longer apply today. There is a third possibility, more exotic and more provocative. Planet 9 may not have been born in our solar system at all. During the period when the Sun was still young and embedded in its stellar birth cluster, it would have been surrounded by thousands of other young stars, all jostling for position in a dense gravitational environment. Simulations have shown that during this period, stars and birth clusters can capture planets from each other through close gravitational encounters. A planet orbiting a neighboring star could, in principle, be gravitationally captured by the Sun during a close stellar passage, ending up in a distant, inclined, eccentric orbit very similar to what Planet 9 is hypothesized to occupy. If this happened, Planet 9 would be, in the deepest possible sense, not originally ours. It would be an interloper, a world born around another star, captured billions of years ago, and now silently orbiting in the darkness as a permanent but alien member of our solar family. The implications of that idea are enough to make a person sit quietly for a while and stare at the ceiling. Even if Planet 9 formed in our own solar system, its presence in the outer system would have had profound effects on the solar system's history that we are only now beginning to understand. Its gravitational influence over billions of years would have shaped the Oort cloud, the vast, spherical reservoir of comets that surrounds the solar system at distances ranging from a few thousand to more than 100,000 astronomical units from the Sun. Comets that occasionally visit the inner solar system, searing their tails across the night sky in brightness that has startled and inspired humans since prehistory, are thought to have been perturbed from the Oort cloud by gravitational nudges from passing stars, the galactic tide, and possibly Planet 9's gravity. In other words, Planet 9, if it exists, may have been influencing the history of inner solar system impacts for billions of years. It may have shaped which comets fell on the early Earth, contributing to the water in our oceans and the organic molecules that seeded the chemistry of life. The ghost world at the edge of the solar system and the origin of life on Earth may be connected through 4 billion years of gravitational physics, a connection so tenuous and so profound that it almost defies contemplation. There is also the question of what Planet 9 would actually look like up close, if we could somehow visit it or bring its features into sharp focus. Based on the mass estimates, roughly 10 times Earth's mass, Planet 9 would be what astronomers call a super-Earth, or perhaps more accurately a sub-Neptune. A world intermediate in size between Earth and Neptune, with no strong analog in our solar system. It would likely have a deep hydrogen-rich envelope surrounding a rocky or icy core. Its surface, to the extent that the transition between its gaseous envelope and its interior can even be called a surface, would be shrouded in darkness. The Sun, from Planet 9's location, would provide only a tiny fraction of the heat and light it provides at Earth's distance. Surface temperatures would hover somewhere between -220 and -230 degrees Celsius, only a few tens of degrees above absolute zero. And yet, Even at these temperatures, a world of this mass retains its own internal heat. Planet 9 would still be slowly radiating energy left over from its formation, the residual heat of planetary accretion that has been bleeding slowly into space for 4.5 billion years. This is actually how astronomers might eventually detect it. Not from its reflected sunlight, which would be almost impossibly faint, but from its thermal emission, the infrared glow of its own residual warmth. If Planet 9 currently lies at the closer end of its orbit, within a few hundred astronomical units of the Sun, the upcoming Vera Rubin Observatory's LSST camera, with its enormous light-collecting area and sensitivity to faint moving objects, would have a real chance of detecting it through both reflected light and thermal emission. If it currently lies at the farther end of its orbit, beyond 600 or 700 astronomical units, detection will require even more powerful next-generation instruments that may not exist for another decade. The Vera Rubin Observatory, located in the Chilean Andes and officially opening its survey operations in the mid-2020s, is widely regarded as the instrument most likely to either confirm or definitively rule out Planet 9. It will survey the entire southern sky repeatedly, building up an enormous database of moving objects in the outer solar system. Its sheer sky coverage means that if Planet 9 is anywhere in the southern sky, which is possible but not certain, given the uncertainty in its orbital parameters, the Vera Rubin Observatory should find it. If it does not appear in the Vera Rubin data within the first few years of operations, that will significantly constrain the parameter space of where Planet 9 can be, possibly ruling out its existence entirely or pushing its location further from the Sun than current estimates suggest. The Chinese Antarctic Survey Telescope, operating from the Domé site in Antarctica, one of the driest and optically stable sites on Earth, is also beginning to contribute to the hunt for outer solar system objects. The unique vantage point of Antarctic observatories, able to observe circumpolar regions of the sky that northern hemisphere telescopes cannot easily access, makes them valuable assets in a search that must cover as much sky as possible. The James Webb Space Telescope, already transforming our understanding of the distant universe with breathtaking images of galaxies at the edge of the observable cosmos, could also in principle be turned toward the outer solar system to image Planet 9 if a precise enough position were known. But the JWST is a pointed instrument, not a sky survey telescope. It needs to be told where to look. Its extraordinary infrared sensitivity would make it capable of detecting Planet 9's thermal emission at distances that would be invisible to ground-based instruments, but only once a candidate position has been identified from survey data. The search and the confirmation would require two different tools, two different observing strategies working in concert. And then there is the remarkable possibility that Planet 9 has already been photographed unrecognized in archival data. The sky has been surveyed repeatedly over the past several decades by a succession of increasingly powerful instruments, from the Palomar sky survey plates of the 1950s and 1960s to the digital surveys of the modern era. Planet 9, if it exists, has left a trail of faint images in these archives. Photons that struck photographic plates or digital sensors, indistinguishable at the time from background noise or transient artifacts. Researchers are now mining these archival datasets with sophisticated machine learning algorithms, teaching neural networks to recognize the distinctive signature of a slow-moving outer solar system object from stacks of old observations. It is possible, genuinely, not just theoretically possible, that Planet 9 has already been captured on glass plates sitting in drawers at an observatory somewhere, waiting to be recognized. This is one of the aspects of modern astronomy that tends to astonish people not working in the field. We live in an era of such unprecedented sky coverage that the discovery of new solar system bodies is increasingly becoming a computational challenge as much as an observational one. The bottleneck is not photons, we have plenty of those. The bottleneck is the ability to sift through petabytes of data and extract the moving, faint, distant objects from an overwhelming sea of background noise. Machine learning, which has revolutionized image recognition in commercial applications, is now being deployed at the frontier of solar system discovery. The algorithm that eventually identifies Planet 9 in archival data may already have been written. It may be running right now on a computing cluster somewhere, working through archived observations that were collected years ago without any suspicion of what they might contain. There is something deeply cinematic about that image. Somewhere in a cold data center, a neural network trained on the morphology of outer solar system objects is slowly, methodically comparing the positions of faint smudges in archival sky survey images, looking for the barely perceptible shift that would indicate a real moving body against the static background of the stars. No human watching. No immediate fanfare. Just mathematics and electricity and stored light, working through the archives of the sky within human patience. And at some point, possibly tomorrow, possibly years from now, a flag will be raised in the code. Anomalous motion detected. Candidate object. Follow-up required. And someone will look at the flagged images and understand immediately what they are seeing, and the world will change. It is worth reflecting on what the confirmation of Planet 9 would actually mean, not just for astronomy, but for our understanding of where we are and what we are part of. Our solar system has been considered relatively well characterized since the discovery of Neptune in 1846. The broad outline, for rocky inner planets, an asteroid belt, for giant outer planets, and a scattering of smaller bodies beyond, has been taught in schools and illustrated in textbooks for generations. The discovery of Planet 9 would rupture that sense of completeness. It would reveal that our own solar system, which we have been studying with increasingly sophisticated tools for centuries, still harbored a major secret at its edge. And not a minor secret. A planet 10 times the mass of Earth is not a footnote. It is a major component of the solar system's gravitational architecture. Its presence would reshape our models of how the solar system formed, how it evolved, and how it came to look the way it does today. It would make us reconsider every detailed computer simulation we have ever run of solar system dynamics, because all of those simulations omitted a gravitational influence that, if real, is not negligible. The tidy story of solar system formation would need to accommodate a new character, one whose origin, whether scattered from the inner system, formed in the outer disk, or captured from another star, remains deeply uncertain. There is also the question of what Planet 9 means for the study of exoplanets, planets orbiting other stars. One of the most consistent findings of the past 3 decades of exoplanet science is that super-Earths and subneptunes are the most common type of planet in the galaxy. Nearly every planetary system we study contains worlds in this mass range. Our own solar system, with its curious absence of planets between Earth's mass and Neptune's mass, has always looked like an outlier in this statistical landscape. The existence of Planet 9 in the far outer solar system would go some way toward making our solar system look more like everyone else's. We just happen to scatter our super-Earth to the remote outer edge rather than leaving it in the warm, bright inner system where it would have been obvious all along. We are not the exception to the rule. We have just been misreading the rule because we did not know where to look. This connects to one of the most profound questions in planetary science: whether the solar system we inhabit is typical or unusual. For a long time, astronomers assumed our system was broadly representative of how planetary systems are organized. Then we started finding exoplanets, and it became clear that our system is actually quite unusual in several ways. The absence of super-Earths close to the Sun, the wide spacing of our giant planets, the relative calm of our dynamical architecture. Planet 9 would not make us typical exactly, but it would close one of the most conspicuous gaps between our solar system and the general pattern seen in the galaxy. It would tell us that the process that produces super-Earths, that most common of planetary outcomes, did operate in our own solar system. The resulting planet was just flung to an extraordinary distance rather than being left in a comfortable orbit close to the Sun. And if Planet 9 is real, what happens next? If Vera Rubin or some other instrument confirms its existence in the coming years, what follows is an extraordinary era of outer solar system exploration. We would immediately want to know its precise mass, its exact orbital parameters, the details of its surface composition. A confirmed position would allow JWST and other infrared telescopes to study it in detail. In the longer term, over decades or perhaps a century, we might contemplate sending a spacecraft to investigate. The distances involved are staggering. Voyager 1, the fastest object ever launched by humanity and the first human-made object to leave the solar system, has been traveling for more than 45 years and has covered about 163 astronomical units. Planet 9 at its closest approach would be 200 astronomical units away. With current propulsion technology, reaching Planet 9 would require many decades of travel time. Next-generation propulsion concepts, nuclear electric drives, solar sails, laser-pushed light sails, could potentially shorten this dramatically, but even with advanced technology, A Planet 9 mission would be a multi-generational endeavor, a project requiring the sustained commitment of civilizations rather than individuals. There is a school of thought in space exploration philosophy that says we should not be discouraged by distances that will require generations to traverse. We have built cathedrals that took centuries to complete. We have planted trees whose shade we will never sit under. A civilization capable of sustaining interest in a cosmic goal across generations would send a spacecraft to Planet 9, wait 50 years for it to arrive, and then spend a decade analyzing the data. The returns would be extraordinary. Direct sampling of a world at the very edge of the solar system, in a region where conditions reflect the earliest, coldest, and most pristine environments of planetary formation, would open entirely new windows onto the history of the solar system and the nature of planetary chemistry at extreme cold. But we are getting ahead of ourselves. Before we can plan a mission, we need to find it. And before we can be certain it is there to be found, we need to continue accumulating the observational evidence that either supports or undermines the hypothesis. This is where the story stands today, at the threshold of potential discovery, with the evidence pointing strongly in one direction but not yet delivering the definitive observation that would silence all doubt. Every field of science has its great open questions, the ones that sit at the edge of current knowledge and generate the most passionate, productive, and occasionally acrimonious scientific debates. In cosmology, it is the nature of dark matter and dark energy. In particle physics, it is the question of what lies beyond the standard model. In planetary science, it is this: does Planet 9 exist? The fact that we do not yet know the answer should not be interpreted as a failure. It should be interpreted as a frontier. And frontiers, in science as in exploration, are exactly where the most interesting things happen. Consider what the discovery would look like in real time. Somewhere, most likely in the data stream of the Vera Rubin Observatory, though possibly in archival mining results or Pan-STARRS data or Subaru images, a slow-moving object will be identified at enormous distance from the Sun. Confirmation observations will be made over the following weeks and months. The orbit will be calculated, and researchers will find that it matches, or does not match, the predictions of the Planet 9 hypothesis. If it matches, the moment of confirmation will be one of the most significant astronomical announcements since the discovery of the accelerating expansion of the universe in 1998. It will make front pages across the world. It will require immediate revision of every textbook chapter about our solar system. It will settle, finally, a debate that has gripped planetary science for a decade, and it will raise an immediate new question. What do we name it? The tradition in planetary nomenclature is to name planets and dwarf planets after mythological figures, following a loose convention of Roman and Greek deities for the major planets. The name Planet 9 is clearly a placeholder, a working title for something that does not yet officially exist. When it is confirmed, the International Astronomical Union will oversee the formal naming process. Brown and Badijan have both acknowledged that they expect the community to be deeply engaged in proposing names. Given the planet's ghostly, distant, barely there quality, known through inference rather than observation, lurking in the dark at the edge of the known, there is something fitting about the suggestion, made by several commentators, that it might deserve a name associated with darkness, the underworld, or the extreme outer limits of mythological geography. Some have suggested Persephone, goddess of the underworld and the seasons. Others have suggested Nemesis, though that name carries baggage from an older and now discredited hypothesis about a companion star to the Sun that periodically sends comets into the inner solar system. Whatever name the community ultimately chooses, it will need to carry the weight of representing the outermost member of our solar family, a world that waited billions of years to be discovered and will now, finally, have a name that humans on Earth will know and say. But here, at the end of this telling, it is worth sitting with the strangeness of the situation we find ourselves in as a species in the 21st century. We have landed robots on Mars and brought samples of asteroids back to Earth. We have photographed the atmospheres of gas giants in extraordinary detail and mapped the surfaces of icy moons down to the scale of individual craters. We have sent probes to the edges of the solar system and beyond, and we have images of Pluto in full color. And yet, right here in our own solar system, there may be a planet we have never seen, a world that dwarfs the Earth in mass and has been orbiting the Sun since before the Earth even formed, that we have only now begun to suspect exists because of the subtle gravitational shadows it leaves on much smaller objects at the fringe. This should be humbling, and it should be thrilling. The solar system is not a solved puzzle. It is not a finished map. It is a live, dynamic, imperfectly understood system that continues to surprise us. Every time we have announced with confidence that we understand its broad architecture, the universe has shown us something we missed. Pluto and its complex, geologically active surface. The extensive moon systems of the giant planets. The Kuiper Belt, whose sheer variety of objects was largely invisible to us before the 1990s. And now, perhaps, a 10th body, a planet by any reasonable definition of the word, orbiting in the darkness beyond all of them. The ghost world, if it exists, has been there all along. Patient, massive, silent, moving in its long, slow arc through the darkness at temperatures that would freeze any instrument we have ever built before it had a chance to work. It has completed perhaps 250,000 full orbits since the formation of the solar system. Every orbit takes 10,000 years. While our entire recorded human history, everything from the first cities of Mesopotamia to the Apollo program, has unfolded in what amounts to less than a single one of its years, Planet 9 has gone around the sun once and barely noticed. We are looking for it. We are looking with the most sensitive instruments our civilization has ever built, scanning the darkest regions of the sky with inhuman patience, writing algorithms to recognize its telltale movement from images taken years and decades ago. We are doing what human beings have always done when confronted with the vastness of the cosmos. We are reaching outward, refusing to be satisfied with the boundaries of the known, insisting that the next question is worth asking and the next discovery is worth seeking. We do not know for certain that it is there, but the math says it probably is. And in the history of astronomy, that is usually a sentence that ends with discovery. The solar system is still speaking to us. We just need to listen carefully enough to catch the whisper. There is a particular kind of scientific patience that this search demands, and it is worth spending a moment understanding what that patience actually looks like in practice, because it illuminates something important about the nature of discovery itself. Mike Brown has described the search for Planet 9 as fundamentally different from other searches he has conducted over his career. When he was hunting for large Kuiper Belt objects, finding Eris, Sedna, Makemake, Haumea, the strategy was relatively straightforward. Survey the sky, look for moving objects, catalog them, determine their orbits. The objects were faint, but they were findable with modern instruments and a systematic approach. Planet 9 is different. It is not just farther away. It is so far away that the ordinary tools of asteroid and Kuiper Belt searching are barely adequate. The reflected sunlight from an object at 500 or 600 astronomical units would be so diminished by the inverse square law that the object would be right at the threshold of detectability for the best existing ground-based instruments. You cannot simply survey and find. You have to build a probabilistic picture from the behavior of other objects, narrow down the region of sky where the planet is most likely to be, and then concentrate observational resources in that region with extraordinary care. Brown has spoken publicly about the frustration and the exhilaration of this kind of work. The frustration comes from the uncertainty. Every observing run on the Subaru telescope produces thousands of images that must be carefully analyzed, and the absence of a detection is ambiguous. You cannot tell from a non-detection whether the planet is not there or whether you simply have not yet looked in the right patch of sky. The orbital uncertainty in the Planet 9 hypothesis is substantial. The planet could be anywhere along hundreds of astronomical units of its predicted trajectory, spread across a significant fraction of the sky. Each null result narrows the search space a little, but the narrowing is slow because the sky is so vast. The exhilaration comes from the moments when a new extreme trans-Neptunian object is found and its orbit turns out to be consistent with the Planet 9 prediction. Every new distant object added to the catalog is another data point, another opportunity to test whether the clustering signal is real or illusory. And when a newly discovered object falls exactly where the Planet 9 hypothesis predicts it should, when its orbit, computed fresh from new observations, places it in the cluster of orbital alignments that first suggested the planet's existence, there is a moment of quiet satisfaction, a sense that the evidence is converging, that the signal is real, that the search is going in the right direction. Konstantin Batygin, for his part, brings to the problem the perspective of a theoretical physicist who is deeply committed to the mathematical self-consistency of the argument. Batygin has been explicit about the fact that, for him, The most compelling aspect of the Planet 9 hypothesis is not any single piece of evidence but the architecture of the argument as a whole. When a single unobserved body can simultaneously explain orbital clustering, the solar obliquity, the retrograde population, and the detached Kuiper belt objects, you are looking at what physicists call an overconstrained system, a system where more evidence supports the hypothesis than is strictly necessary to establish it. In physics, overconstrained systems are powerful precisely because they offer many independent ways to be wrong. If Planet 9 did not exist but its postulated properties just happened to explain the orbital clustering by coincidence, it would still need to coincidentally explain the solar obliquity independently, and the retrograde population independently, and the detached Kuiper belt objects independently. The probability of all these coincidences occurring simultaneously without an underlying physical cause is effectively zero. The logical weight of convergent independent evidence is enormous. This is the same argument structure that made the case for dark matter so compelling to physicists. We cannot see dark matter. We have never directly detected it. And yet it is required to explain the rotation curves of galaxies, the velocity dispersions of galaxy clusters, the large-scale structure of the universe, the cosmic microwave background power spectrum, and the formation of the earliest galaxies. Each of these phenomena independently points to the same missing mass. The probability of all of them being explained by anything other than a real, massive, unseen component of the universe is effectively zero. And yet, like dark matter, Planet 9 has so far eluded direct detection. The parallel is uncomfortable and instructive. What would it actually mean for Planet 9 to not exist? If all the surveys have been completed, all the sky coverage accounted for, all the observational biases characterized, and there is still no detected planet, what then? It would mean one of several things. It could mean that the clustering is entirely an artifact of observational bias, that the objects we have found are not a representative sample of the outer solar system population, and that with a truly unbiased survey the orbital alignments vanish. It could mean that some other, less dramatic mechanism, perhaps the collective gravity of the known Kuiper belt population itself, or the secular influence of the galactic tide, is responsible for the observed patterns. Or it could mean something genuinely unexpected, a new physics of orbital dynamics that we do not yet understand, or the gravitational influence of some other kind of object entirely. Some researchers have proposed models in which the outer solar system is shaped not by a single massive planet but by a disk of smaller material, a broad annular structure of icy bodies whose collective mass amounts to a few Earth masses and whose distributed gravity could produce some of the orbital effects attributed to Planet 9. This disk model is difficult to reconcile with all the observed phenomena, particularly the solar obliquity and the retrograde population, but it cannot be definitively ruled out with current data. The outer solar system is not well enough characterized for us to be certain what is and is not there. There is also the tantalizing possibility that the story of the outer solar system is not yet finished being written, that additional discoveries in the next few years will either dramatically strengthen the Planet 9 case or open entirely new lines of inquiry that redirect the search in unexpected directions. Astronomy has a long history of surprises that upend prior understanding just when the existing framework seemed most secure. Think about how the discovery of the Kuiper belt itself unfolded. For decades after the identification of Pluto in 1930, the region beyond Neptune was thought to be largely empty. Pluto and perhaps a few similar bodies, but nothing resembling a population of objects. The theoretical prediction of a Kuiper belt, made independently by Kenneth Edgeworth in 1943 and Gerard Kuiper in 1951, was generally considered speculative and was not taken seriously by most of the community. Then, in 1992, astronomers David Jewett and Jane Liu found 1992 QB1, the first confirmed Kuiper belt object beyond Pluto, and the floodgates opened. Within a decade, thousands of objects had been catalogued in the Kuiper belt, and it became clear that Pluto was not a lonely outpost but a member of a vast population of small worlds that had been invisible simply because no one had looked with sufficient sensitivity. Could the same paradigm shift happen with Planet 9? Is it possible that, within a decade, the existence of a massive distant planet will seem as obvious and well-established as the Kuiper belt does today? Something we will look back on and wonder why it took us so long to find? The answer is almost certainly yes, if Planet 9 is real. The tools are coming. The surveys are underway. The algorithms are being trained. The question is not whether we will eventually have the capability to either confirm or rule out the hypothesis. We will. The question is how long we will have to wait and what we will learn in the process. And waiting in science is never passive. The years spent searching for Planet 9 have produced enormous dividends in our understanding of the outer solar system regardless of whether the planet itself is found. The catalogs of extreme trans-Neptunian objects have grown dramatically, from a handful in 2014 to dozens today, and each new object is a fossil record of the outer solar system's dynamical history. The surveys conducted in the course of the Planet 9 search have turned up new moons of Jupiter and Saturn, new near-Earth asteroids, new interstellar objects, the whole diverse and surprising population of solar system bodies that would have remained invisible without the systematic sky coverage that the Planet 9 hunt demanded. Science rarely delivers only what it was looking for. Let us talk about what the outer solar system actually looks like, because the setting of this story is almost as dramatic as the story itself, and most people have never been given a true sense of the physical environment out there. The inner solar system, the region we tend to think of when we picture the solar system, is actually a tiny fraction of the total volume. The 8 planets, including Neptune, all fit within a sphere roughly 60 astronomical units in radius. That sounds large, but the full outer boundary of the solar system, the region where the sun's gravitational influence finally yields to the gravitational influence of other stars, extends to perhaps 100,000 astronomical units. The solar system is not a disk with a neat edge. It is a sphere, almost unimaginably vast, whose outer regions are occupied by the Oort cloud, a reservoir of trillions of icy bodies distributed in a spherical haze extending almost a quarter of the distance to the nearest star. In the region between 30 and about 100 astronomical units, the Kuiper belt, the physical conditions are extreme in ways that challenge engineering. Temperatures are so low that common substances on Earth would be completely solid. Water is rock. Carbon dioxide is frost. Methane condenses out of the tenuous gas phase and freezes onto the surfaces of small bodies. The chemistry operating in these conditions is strange and rich and poorly understood. Complex organic molecules, tholins, named by Carl Sagan who studied them extensively, form in the outer solar system through the slow irradiation of ices by cosmic rays and solar ultraviolet radiation. The reddish surfaces of many Kuiper belt objects, including the striking red expanses on Pluto's moon Charon and the distinctive coloring of many trans-Neptunian objects, are the result of this radiation-driven chemistry operating over billions of years. In this environment, Planet 9 would be an extraordinary object, cold beyond most instruments' ability to function, dark beyond easy imaging, massive enough to gravitationally sculpt the smaller objects around it into patterns that we can detect from Earth. Its surface, if it has a true surface beneath the hydrogen envelope, would be a landscape of frozen hydrogen and helium ices at temperatures barely distinguishable from absolute zero, subject to bombardment by cosmic rays unshielded by any meaningful magnetic field at such low activity levels. There would be no sunlight worth speaking of, just the faintest stellar light, orders of magnitude dimmer than what illuminates the moon at night. And yet, strange as it sounds, this is not the most remote environment we know of in the solar system. The Oort cloud objects, those distant ice bodies at tens of thousands of astronomical units, exist in conditions that are genuinely interstellar in character, beyond the heliosphere, subject to the interstellar medium's radiation environment, moving in orbits that are perturbed directly by the gravitational tidal field of the Milky Way galaxy rather than being primarily governed by the Sun. They are solar system objects in a technical sense, but interstellar objects in their environmental context. Planet 9, by contrast, at a few hundred to perhaps 1,200 astronomical units, is solidly within the heliosphere for much of its orbit, subject to the Sun's particle environment and magnetic field, gravitationally bound tightly enough that its orbit is well-defined and predictable over billions of years. In 2017, the discovery of the interstellar object 1I/Oumuamua, the first confirmed object from another solar system to pass through ours, added a new dimension to thinking about the outer solar system and objects like Planet 9. Oumuamua arrived from interstellar space, passed through the inner solar system on a hyperbolic trajectory, and departed. Its properties, particularly its non-gravitational acceleration, which appeared to push it away from the Sun faster than gravity alone could explain, sparked enormous debate. Some researchers proposed that it was a fragment of a solid hydrogen iceberg. Others proposed it was a thin solar sail, perhaps a technological artifact of unknown origin. The more mundane explanations involved outgassing of volatile material being heated by solar radiation. Whatever Oumuamua was, its discovery established definitively that our solar system is not sealed off from the broader galactic environment, that objects from other stellar systems can and do pass through, and that the outer solar system may interact with the interstellar medium in ways we are only beginning to understand. The second confirmed interstellar object, 2I/Borisov, discovered in 2019, looked much more like a conventional comet. It showed a clear coma and tail suggesting active outgassing, and was less controversial in its interpretation. But its discovery confirmed that interstellar visitors are not extremely rare events. The space between stars is not empty. It is populated by a background population of objects, ejected from the billions of planetary systems in the galaxy, drifting between the stars on timescales of millions of years. Our solar system sweeps through this background population continuously, occasionally capturing objects gravitationally, occasionally being grazed by hyperbolic visitors like Oumuamua and Borisov. This context matters for Planet 9 because, as noted earlier, one of the possible origins of Planet 9 is capture from another star during the Sun's youth in its birth cluster. The existence of interstellar objects shows that planetary material does cross stellar boundaries. The theoretical models suggest that capture events were much more common when stellar densities were high in the birth cluster than they are today in the field. Planet 9, if it was captured, would be a permanent resident. It has been gravitationally bound for 4 billion years and is not going anywhere. But its chemistry, its isotopic composition, possibly its internal structure, might reflect its formation around a different star, different proportions of heavy elements, different ratios of stable isotopes, properties that could in principle be measured by a sophisticated flyby mission and compared to what we would expect for a body formed in our own solar system. The philosophical weight of this possibility is extraordinary. We are discussing a world that may have formed around a star that burned out billions of years ago, a star whose other planets were scattered into the interstellar void when its stellar evolution destabilized the system, a world that was alone in interstellar space for perhaps hundreds of millions of years before being gravitationally captured by the young sun and finding its place, however distant and cold and dark, in what we now call our solar system. If that story is true, then Planet 9 has been in our solar system for so long that it is, for all practical purposes, ours. But in some deep sense it came from elsewhere, born in a different stellar nursery under different conditions, carrying within its frozen bulk the chemical memory of its true origin. When we think about the concept of home, the solar system as home, Earth as home, it becomes a more interesting concept in light of Planet 9. We tend to think of the solar system as a fixed and bounded thing, its members determined at the time of formation and unchanged since. But the solar system is more porous than that. Objects leave it, scattered by gravitational encounters into interstellar space. Objects enter it, captured from the ambient background population or perhaps from specific passing stars. The membership of our solar system, at the finest level of detail, is not a static list but a dynamic population, changing on timescales of millions to billions of years, its boundaries blurred by the gradual exchange of material with the broader galaxy. Planet 9, whether native or captured, represents the outermost known member of this community, assuming it exists. And its eventual discovery would not just add a member to the list. It would force us to look at the list differently, to see the solar system not as a closed and thoroughly cataloged family of worlds, but as a dynamic, complex, and still surprising system whose secrets continue to yield to patient, rigorous, creative inquiry. The history of planetary discovery is also the history of our expanding sense of what the solar system is. Each new world found beyond the previous boundary has enlarged the concept. Mercury, Venus, Mars, Jupiter, Saturn, visible to the naked eye since antiquity, familiar to every ancient stargazer. Uranus, found by William Herschel in 1781 with a telescope, the first planet discovered in the modern era, instantly doubling the known size of the solar system. Neptune, found in 1846 by mathematical prediction, demonstrating for the first time that gravity could be used to infer the existence of unseen objects. Pluto, discovered in 1930, later reclassified, still beloved by a public that refuses to accept its demotion. Eris, Makemake, Haumea, Sedna, the new generation of distant worlds that revealed the Kuiper Belt as a place of astonishing richness and variety. And now, perhaps, Planet 9, a world that would not extend the edge of the solar system. The Oort cloud is already known to exist at far greater distances, but would extend the domain of large planetary bodies to distances previously thought to be the exclusive territory of much smaller objects. Its discovery would say something profound about the range of environments in which a world can exist, the range of distances from a star at which a planetary body can orbit stably, and the extraordinary variety of dynamical histories that solar systems can experience over their multi-billion-year lifetimes. There is a generation of astronomers and planetary scientists who will either make this discovery or be defined by the search for it. The researchers working today on the observational campaigns, the graduate students reducing Subaru images, the postdocs running orbital simulations, the senior astronomers planning the next survey strategies, are doing the kind of science that will be discussed in textbooks decades from now, regardless of whether they find the planet or not. If Planet 9 is real and is found, the discoverers will join a short and distinguished list: Herschel, Adams, Leverrier, Tombaugh, Jewett, and Liu. If Planet 9 turns out not to exist, and the evidence is eventually explained by other means, the search will still have been enormously productive, yielding a far richer understanding of the outer solar system than we had before. Science is not diminished by the absence of a discovery. The null result, the careful, systematic, thorough conclusion that something predicted does not exist, is itself a discovery, one that redirects inquiry in productive new directions. The failure to find a luminiferous ether was not a failure of science, but one of the most important results in the history of physics, directly clearing the ground for special relativity. The absence of the postulated modifications to general relativity in precision solar system tests was not a failure but a vindication of Einstein's framework at extraordinary precision. If the Vera Rubin Observatory surveys the entire sky and finds no Planet 9, that result will constrain our understanding of the outer solar system profoundly and will demand an explanation, and seeking that explanation will produce new science. But the search is not over yet. It has barely begun in the timescale of serious astronomical surveys. The Vera Rubin Observatory represents a qualitative leap in survey capability. 10 years of systematic sky coverage at sensitivity levels that will probe the outer solar system to distances and depths never previously reached. The data volume it will produce is so large that traditional analysis pipelines are inadequate, and the field has had to develop entirely new computational infrastructure: multi-petabyte databases, distributed processing systems, machine learning pipelines designed from the ground up to handle astronomical volumes of sky survey data. We stand, right now, at the beginning of the most capable era of outer solar system exploration in history. The tools have never been better. The analytical methods have never been more sophisticated. The theoretical framework has never been more carefully developed. The community of researchers working on the problem has never been larger or more internationally diverse, with teams from the United States, Japan, Chile, Canada, China, and Europe all contributing to the search. And somewhere, in the darkness beyond the edge of everything familiar, a world, cold and ancient and massive and silent, may be waiting to be found. It does not know we are looking. It has no awareness of the telescopes sweeping the sky, the algorithms combing through the archives, the scientists debating its existence in conference rooms and on preprint servers. It is simply moving, as it has been moving for 4.5 billion years, tracing its long ellipse through the darkness, indifferent to us, patient in a way that only an astronomical object can be patient, which is to say absolutely, unconditionally, eternally patient. We are not patient in the same way. We are curious, and curious creatures cannot be still. We look, we measure, we calculate, we argue, we look again. We have been doing this for as long as we have been the kinds of beings who look up at the sky and wonder what is out there. We did it when we did not have instruments, when we tracked the movements of planets across the sky with only our eyes and the disciplined application of geometry. We did it when we made our first telescopes and turned them on the heavens and found moons circling other planets and other worlds turning in the light of the sun. We did it when we mounted instruments on rockets and shot them beyond the atmosphere to see the sky without the blurring interference of air. And we are doing it now with tools of extraordinary power and subtlety, aimed at the farthest reaches of our own solar system. The ghost world may be real. The gravitational evidence whispers it. The mathematics insists it. The statistics demand, not with certainty but with the compelling force of converging independent probabilities, that something is out there, shaping the orbits of the outermost objects, tilting the sun's equator with its long gravitational leverage, populating the retrograde reaches of the outer solar system with backward orbiting exiles. And when it is found, if it is found, it will not merely be a scientific discovery. It will be a moment of recognition. The recognition that the solar system is larger and stranger and more complete than we knew. The recognition that our cosmic home, for all our centuries of diligent study, still had secrets to keep. The recognition that the universe is not done surprising us, and probably never will be. That is the most important thing Planet 9 represents, whatever the outcome of the search. Not just a planet, not just a gravitational anomaly, not just a solution to a statistical clustering problem in the outer Kuiper belt. It represents the edge of the known, that permanent, shifting frontier where human knowledge ends and the darkness begins, and where, if you look carefully enough, you can sometimes see something looking back. We are looking. We will keep looking. And one day, perhaps soon, the darkness will answer. To fully appreciate why Planet 9 has captured the imagination of scientists and the public alike in a way that few astronomical hypotheses have in recent memory, it helps to understand something about the particular moment in history in which we are living. We are, right now, in what future historians of science will almost certainly characterize as a golden age of solar system exploration. In the past decade alone, we have received close-up images of Pluto, revealing a world of extraordinary geological complexity, with mountains of water ice reaching thousands of feet, plains of nitrogen ice that flow slowly like glaciers, haze layers in a nitrogen atmosphere, and geologic features whose origin remains debated. We have orbited Ceres, the largest object in the asteroid belt, and found bright spots in a crater that turned out to be deposits of sodium carbonate precipitated from subsurface brine, evidence of a geologically active world we never expected to find at that distance from the Sun. We have watched the New Horizons spacecraft fly through the Kuiper belt beyond Pluto and image Arrokoth, a contact binary Kuiper belt object whose gentle, lobe-on-lobe shape records the soft collision of two primordial planetesimals and provides direct evidence of how the building blocks of the solar system assembled themselves in the cold outer disk billions of years ago. We have, in other words, been humbled repeatedly by worlds we thought we knew. Pluto was supposed to be a dead, frozen rock. It is not. Ceres was supposed to be inert and undifferentiated. It is not. Arrokoth was supposed to tell us about collisional fragmentation. It told us about gentle accretion instead. The lesson of recent solar system exploration is consistent and unmistakable. Worlds surprise you when you look at them closely. The preconceptions formed from a distance dissolve when the data arrive, and what replaces them is stranger and richer than what was assumed. Planet 9, if found, will almost certainly follow this pattern. Whatever we think it is, a cold, dark, geologically inactive super-Earth drifting alone in the frozen dark, the reality will be more interesting. Worlds of sufficient mass retain internal heat. Worlds with sufficient chemistry develop surface processes. Worlds with sufficient gravitational fields sculpt the material around them in ways that will take decades of observation to fully characterize. Planet 9, at 10 Earth masses, is not a small object. It has had 4.5 billion years to evolve. Its interior, possibly differentiated into a metal-like core, a silicate mantle, and a deep hydrogen-rich envelope, has been cooling slowly since its formation, possibly driving convection in its interior that would have expressed itself on the surface as tectonic or cryovolcanic features. There may even be, in the deep interior of Planet 9, a liquid water layer. This is not as exotic as it sounds. Neptune and Uranus are both thought to have layers of hot, pressurized water, sometimes called warm ice or superionic water, deep in their interiors, where the pressure is so extreme that water molecules retain their lattice structure, but protons flow freely through the lattice in a kind of ionic fluid. A world of 10 Earth masses, depending on its exact composition and thermal history, might maintain similar conditions. The extreme cold of the surface would be irrelevant to what happens in the deep interior, where the pressure and residual heat from formation provide the necessary conditions for unusual material states. None of this implies life. The conditions in a high-pressure deep interior without a liquid water surface layer connected to chemistry and energy gradients are not conducive to the kind of processes we associate with biology. But it is a reminder that the interior of a massive cold outer planet is not simply a frozen rock. It is a dynamic, high-pressure, chemically active environment that we do not yet understand well. The composition of Planet 9's atmosphere, the thin outer envelope of gas that would surround the planet, would be determined by its thermal evolution and its distance from the Sun. At a few hundred astronomical units, the Sun's radiation is too weak to heat the atmosphere significantly above the background temperature set by the cosmic microwave background, about 2.7 Kelvin, the residual glow of the Big Bang, the faintest possible background warmth pervading all of space. Planet 9's upper atmosphere would be only marginally warmer than this. Hydrogen and helium, being light, would slowly escape the atmosphere over geological timescales through a process called atmospheric sputtering driven by the solar wind and cosmic rays. Heavier molecules, water vapor, methane, ammonia, would be frozen out almost completely, precipitating onto the surface. The thin atmosphere that remained would be predominantly hydrogen and helium, the simplest and most abundant elements in the universe, the primordial stuff of stars and galaxies from which all complexity eventually emerged. And here, in this cold simplicity, there is something almost meditative about Planet 9. It is a world stripped to essentials. No sunlight worth the name, no significant atmosphere, no geology driven by solar heating. Just the slow internal cooling of a world formed at the dawn of the solar system, orbiting in the dark, governed by its own physics and the distant gravitational field of the Sun. It represents the solar system at its most elemental, matter organized into a planetary body under nothing but gravity and chemistry, far from any star, behaving according to laws that are the same everywhere in the universe. When we discover it, I say when, not if, because the history of science strongly suggests that a hypothesis supported by this much convergent evidence tends to eventually be verified, it will represent the closing of a chapter that has been open since the discovery of Neptune. Neptune was the planet that established the principle that gravity could reveal unseen worlds through its influence on the motions of seen ones. Planet 9, if confirmed by the same principle applied with modern tools to the behavior of distant Kuiper belt objects, would represent the most dramatic application of that principle since Adams and Leverrier independently calculated the position of Neptune from the residuals in Uranus's orbit in the 1840s. It would be, in the deepest sense, Newtonian physics, the same physics that allowed us to land on the moon and send probes to Pluto, doing what it does best, turning the invisible into the visible through the universal language of mathematics. Newton himself, who formulated the law of universal gravitation in the 17th century, could not have imagined that his equations would one day be used to predict the existence of a world so remote that light from the sun takes almost a day to reach it. But the equations work at every scale, from the fall of an apple to the orbit of a hypothetical super-Earth at 1,000 astronomical units. The precision of the prediction, the elegance of the method, the patience of the search, these are all expressions of a scientific tradition that has been building for 400 years since the first telescopes were turned toward the sky. There is also, in the Planet 9 story, something that speaks directly to contemporary scientific culture and its relationship with the public. The search for Planet 9 has been unusually transparent and public-facing. Brown and Badigian have blogged, given public lectures, appeared on podcasts, and engaged with amateur astronomers in ways that have made the search genuinely participatory in character. The Backyard Worlds, Planet 9 project, which ran as a citizen science initiative through the Zooniverse platform, enlisted more than 150,000 volunteers to examine images from NASA's WISE infrared sky survey, looking for faint moving objects that automated algorithms might have missed. Human eyes, it turns out, are still surprisingly good at recognizing unusual patterns in image data, and the project produced real scientific results. Dozens of new cold brown dwarfs were found by citizen scientists, and new candidates for outer solar system objects were identified and submitted for professional follow-up. This is science at its most democratic. The search for the ninth planet is not happening in a sealed laboratory accessible only to credentialed specialists. It is happening in the open, with data shared publicly, methods published in peer-reviewed journals that are increasingly available as open access, and analysis tools released as open source code. Amateur astronomers with sufficiently capable instruments, backyard telescopes of 30 centimeters or more with cooled CCD cameras, cannot realistically detect Planet 9 itself, but they can and do contribute to the characterization of Kuiper belt objects and the verification of candidates identified by professional surveys. The community of people engaged with this search, in one way or another, numbers in the hundreds of thousands. And the public interest is not merely passive. When Brown and Badigian published their 2016 paper, the response from the public was extraordinary and immediate. People wanted to know, Is there really a ninth planet? Can we see it? When will it be found? What will it be named? The questions poured in through social media, email, in comment sections across the internet. The hunger for the answer was palpable, and it was not merely the hunger of curiosity. It was the hunger of people who felt that this discovery, if made, would mean something not just scientifically but personally, cosmically, in terms of how they situated themselves in the universe. There is a reason that planetary discoveries resonate with people in a way that, say, advances in molecular biology or condensed matter physics rarely do. Planets are places. They are worlds. Even the coldest, darkest, most uninhabitable world in the outer solar system is still a place. A location in space that has a surface, however frozen, however dark, that could in principle be stood upon, a world with its own sky, its own geology, its own history stretching back billions of years. The discovery of a new planet is, in the deepest sense, the discovery of a new place in the universe. And human beings are, fundamentally, creatures of place. We care about places. We name them, map them, imagine them, and feel something when we learn they exist. The discovery of Planet 9 would give us a new place. A strange, cold, remote place that most of us will never visit and that no human will visit in the lifetimes of anyone currently alive. But a place nonetheless. A real location in space, massive and old and there, going around the sun on its long dark orbit, part of our solar system, part of our cosmic address, part of the context in which all of human history has unfolded without our knowing it was there. And perhaps that is the most extraordinary aspect of the whole story. Not the mathematics, impressive as it is. Not the technology, remarkable as it is. Not the history of the search, fascinating as it is. The most extraordinary aspect is the simple fact that there may be, right now, a world larger than Earth orbiting our sun at distances that dwarf everything familiar to us, and we have been living our entire civilizational history without knowing it was there. Empires have risen and fallen. Languages have been born and died. The entirety of recorded human knowledge has been assembled. And through all of it, Planet 9, if it exists, has been quietly making its way around the sun, unmeasured, unnamed, unnoticed, patient in the way that only a planet can be patient. The universe does not keep its secrets forever. They yield, one by one, to curiosity and instruments and mathematics and the peculiar human refusal to accept that the boundary of the known is the boundary of the real. We have been pushing that boundary outward for as long as we have been human. We will keep pushing it. And somewhere in the darkness of the outer solar system, a world waits for the moment when the pushing finally reaches it. That moment may be closer than we think. There is one more dimension to this story that deserves serious attention, and it concerns the nature of certainty itself in the age of modern science. We live in a culture that often mistakes confidence for correctness, that treats the provisional nature of scientific knowledge as a weakness rather than a strength. Planet 9, for all the excitement it has generated, has not been confirmed. It is a hypothesis, the best current hypothesis for explaining a set of observations, supported by substantial statistical and theoretical evidence, but still a hypothesis in the formal scientific sense. And there are scientists who are not convinced. This skepticism is not anti-science. It is science. The community of people working on the outer solar system is not monolithic, and the disagreements within it are healthy and productive. Researchers who have argued that observational bias explains the clustering signal, people like Pedro Bernardinelli, Corey Shankman, and their collaborators are not obstacles to progress. They are participants in the process of verification and falsification that is what science actually is. Their work has forced Brown and Badigian to be more rigorous in accounting for survey biases. Their critiques have sharpened the argument. Science advances not through consensus by acclamation but through the adversarial process of competing hypotheses fighting for the support of data, and the winner is the hypothesis that survives the most rigorous challenge. The prediction of Planet 9 survives, for now. It has been refined with each new data point, constrained with each new survey, tested against each new discovery of extreme trans-Neptunian objects. It has not been falsified, and the predictions it makes for the Vera Rubin Observatory data, the specific patterns of orbital clustering that should be visible in a truly unbiased sky survey of the outer solar system, will provide the most direct test of the hypothesis that has yet been available. Within a few years of Vera Rubin's full operations, we will have our answer, or at least a dramatically more constrained version of the question. This is one of the rare situations in science where a definitive answer appears to be within reach on a human timescale. Many of the great open questions in fundamental physics, the nature of dark matter, the origin of the matter-antimatter asymmetry, the mechanism of inflation, may not be definitively answered in any individual scientist's lifetime because the experiments required to test them are extraordinarily difficult or the theoretical predictions are insufficiently precise. Planet 9 is different. It makes specific, falsifiable predictions about the distribution of observable objects in the outer solar system. The Vera Rubin Observatory will conduct the definitive test of those predictions. The answer, yes, the planet exists, or no, it does not, is coming. That kind of scientific narrative with a clear question, a clear prediction, a clear imminent test, and a clear forthcoming answer is relatively rare in modern science at the frontier. Most frontier science operates in a regime of gradual, incremental progress, where questions are never fully answered but only better constrained. The Planet 9 question has a binary quality to it. The planet is there or it is not. That gives the story a dramatic structure unusual in science but familiar in all other kinds of human narrative. We are, in other words, approaching the climax. The instruments are ready. The surveys are running. The algorithms are processing. The prediction is specific enough to be tested. And sometime in the coming years, the data will tell us, with a clarity that leaves no room for further doubt, whether we have a ninth planet or whether we need to find another explanation for the anomalies we have been puzzling over. The answer, whatever it turns out to be, will teach us something profound about the solar system and about the process of scientific discovery itself. If Planet 9 is found, it will be one of the greatest confirmations of mathematical prediction in the history of planetary science, a triumph of the method that Newton invented and astronomers have been applying ever since. If it is not found, it will force a rethinking of how we understand the outer solar system at a level of detail we have never previously attempted, and it will open new questions that will drive the next generation of outer solar system research. Either way, the search will not have been wasted. Either way, we will know more than we knew before. Either way, the universe will have spoken and we will have listened, and science will have worked exactly as it is supposed to work. Imperfectly, incrementally, but ultimately honestly, ultimately effectively, ultimately bringing us closer to a true understanding of the place we inhabit. We are 9 planets or 8 planets or something in between. We are a solar system still revealing itself to us. We are a civilization young enough to still be learning the basic geography of our own cosmic neighborhood, but old enough to have developed the tools and the will to find what remains to be found. The darkness holds the answer. We are going to find it. And when we do, it will not just be the story of a planet. It will be the story of what human curiosity, at its best and most relentless, can accomplish. When we refuse to accept that the edge of what we can see is the edge of what is there, when we trust the mathematics even when the object it describes has never been photographed, when we point our instruments at the emptiest and darkest parts of the sky because the equations tell us to look, and when we are patient enough to wait for the darkness to show us what it has been hiding for 4.5 billion years. That patience, that refusal to be satisfied with the boundaries of the known, is perhaps the most fundamentally human thing there is. It built the pyramids and wrote the symphonies and sequenced the genome and put footprints on the moon. And it will find Planet 9. If it is there, probably is. Let us end, as all good documentary films end, not with a summary but with a perspective, a final widening of the frame to place the search for Planet 9 in its largest possible context. We are living beings on a rocky planet orbiting a middle-aged star. Our star is one of perhaps 2 to 400 billion stars in the Milky Way galaxy. The Milky Way is one of perhaps 2 trillion galaxies in the observable universe. Within this staggering enormity, the question of whether our solar system has 8 planets or 9 is, by any objective cosmic reckoning, an utterly local concern. It matters to nothing beyond our solar system. The answer changes nothing about the large-scale structure of the universe, the rate of cosmic expansion, the distribution of matter and energy across the cosmos. In the grand arithmetic of existence, a planet more or a planet less in one unremarkable solar system in the outer arm of one unremarkable galaxy is a rounding error so small it does not even register. And yet we search. And yet the question matters to us with an intensity that is completely disproportionate to its cosmic significance. Because we are not cosmic accountants tallying up planets across the universe. We are creatures trying to understand the place that is ours, the small, specific, intimate corner of an incomprehensibly large universe that we were born into and will die in and call, with a kind of touching parochialism, home. The solar system is home. Not just Earth, though Earth is the home of everything we have ever known directly. The solar system as a whole, with its sun and its planets and its moons and its comets and its asteroids and its Kuiper belt and its Oort cloud and possibly its distant ninth planet. This is the volume of space that gave rise to us, that shaped the context in which life on Earth evolved, that has been the stage for the entire drama of biological and human history. To not know the full membership of this family of worlds, to be unaware that one of its members has been orbiting the sun in silence since before the first single-celled organisms appeared in the warm, shallow seas of early Earth. This is not just an astronomical oversight. It is a gap in our self-knowledge. Because knowing our solar system is a form of knowing ourselves. Understanding where we are, what neighborhood we inhabit, what objects share our cosmic address, what gravitational influences have shaped the environment in which we live, is a form of orientation in the universe. It is the cosmic equivalent of knowing your neighbors, your city, your country. Most of us will never travel to the outer solar system. Most of us will live and die within a few hundred miles of where we were born, on a scale that makes even the nearest planet seem impossibly remote. But knowing the solar system exists, knowing its members and their properties and their histories, situates us in the universe in a way that is genuinely meaningful, genuinely orienting, genuinely enlarging of the sense of what we are and where we are. Planet 9, if it exists, is part of our neighborhood. It has been part of our neighborhood since long before there was a neighborhood to call ours. It was orbiting the sun when the first amino acids were assembling in the primordial oceans. It was orbiting the sun when the dinosaurs dominated the Earth. It was orbiting the sun when the first Homo sapiens looked up at the night sky and wondered what they saw. It has moved through less than 0.1% of its orbit in all of recorded human history. When the New Horizons spacecraft reaches its ultimate limit and finally falls silent in the deep dark, Planet 9 will still be there, still moving, still shaping the outer solar system in its slow, patient, gravitational way. We are small and brief, and the universe is vast and old. This is not a reason for despair. It is a reason for wonder. The universe is vast and old, and we are small and brief, and we have nevertheless managed to suspect the existence of a world larger than Earth at a distance 1,200 times the distance to the Sun, based on the behavior of a handful of frozen objects at the edge of the solar system. We have done this with mathematics and telescopes and computation and a relentless refusal to look at the sky and be satisfied with what we can immediately see. That is something. That is, arguably, everything that matters about what we are as a species. Not the wars, not the politics, not the noise and fury and confusion of human history. The upward gaze, the sustained attention, the willingness to let the universe be the teacher, the patience to wait for data that may not arrive for years or decades, the intellectual honesty to follow the mathematics wherever it leads, even when it leads into the darkness. Planet 9 is out there, or it is not. Either way, we are looking. Either way, we will find the answer. Either way, the search has already taught us something important about where we live and how we know it. That is what science is. That is what it has always been. And in the darkness beyond the edge of the solar system, the next chapter is waiting to be written.